Hello, class. Let's break down how to solve this three-dimensional equilibrium problem. So I'm going to keep this high level because getting into the weeds on this can take a long time. And this be the kind of the similar detail if you had a problem like this on the test that I kind of expect. So we have this crate that's being suspended by the system of springs and cables. Looks like I've got two springs and a cable here holding this in equilibrium. I'm going to start by thinking about what we need to find. In this particular case, the objective is find the stretch in each of these springs. So we need to find, let's call it stretch in A and stretch in B to keep this in equilibrium. So in order to find that, I've got to find the force in each of these. So I've got to find this equilibrium first. So let's start with that. If I think about a free body diagram of particle at O, we're going to see the weight of this crate here, which we're given. That's a known. We're going to have some force in the spring at B. And looking at that, it's going to be in the negative x-axis. So I'm going to go ahead and put that I hat there to tell me the direction of that. I've also got a spring force in the A direction, which is in the negative y. And I've got this force acting towards C. Let's call this tension C. And that one is acting in a particular direction. Now I drew it in this way, but actually looking at this, I see there's a parallelogram here. So let me correct that. Working fast here, so I made a little mistake. Let's just correct that. That's actually occurring in this XY direction here. So let's get that drawn in here. Let's draw it. I'm going to bring the drama a little bit. And that's part of the reason why it's kind of coming off at this weird angle here. Its direction is based off of C, and the C location is given here. The X coordinate, which is parallel to X, is 6. The Y coordinate, which is parallel to Y, is 4. And our Z component is 12. That's going to give us tension C, and I've drawn it in this area here. So thinking about that, our first step after we do our free body diagram, so step 1 was kind of our free body diagram and thinking about where all these go. Step 2 is to find the directions of all of these. Now A and B are already given, and I know the direction for weight as well because we know that's got to act straight down. I'll write that as W, negative weight down. Step 2 is going to be finding the direction for TC. I need to find this TC vector. So to find the direction of TC, I'm going to need to find the RC, which is given here, right? 6, 4, 12, that's our RC vector. If we have that, then we can find our direction, our unit vector C, which is going to be the RC vector that we found above divided by its magnitude. Its magnitude is the sum of the squares of its components, Rx, Ry, and Rz squared, which would be 6, 4, and 12 squared respectively. And I think that actually ends up being, I think that's actually comes out to a nice easy square, 36 plus 12, or sorry, 36 plus 16 plus 144 is actually 16. It's one of those Pythagorean triples here. So that actually is pretty easy to find. So now I've got my unit vector to find the force for that. Well, I can't find that directly, but I know the force of that C. Force C is just going to look like the magnitude FC, which we haven't found yet, times its unit vector, which we found above. Now, in this case, I've got 1, 2, 3 unit vectors, or 3 unknowns, and I got 3 equations. I've got everything I need to solve this. call that step 3. Step 4 is thinking about which equations we want to use. So in this case, because we have A and B kind of acting in those primary directions, this is an easier one to solve. I can look at that and go, okay, if I think about the direction with the least unknowns, TC shows up in all of them, right? A was only in the Y direction, B is only in the X direction. So I might want to start with the sum of forces in the Y first, or sorry, in the Z first, that vertical direction. By doing the sum of forces in the Z, I know that this is my only unknown. So from that equation, I will get TC directly. And then from the other equations, like if I do sum of forces in the X, now that I have TC, my only unknown is going to be force B, and my only force and the Y is going to be force, the magnitude of FA. Now my goal was to find the stretch length here. So I'm pretty close. I think step 4, so step 4 you might describe that as the equations of equilibrium. Equations of equilibrium. The other one, the next step would be to find the stretch. And I like to define stretch as change in S or change in length. That'll help me get this correct. So the stretch that I need is going to be based on the force, right? Remember that the force in any spring is going to be K times its stretch. And I have the K constant. The K that's given here. That's 300 Newton meters. So in order to find the stretch, all I need to do is stretch is just going to be the force in each of these divided by K. So if I want to find stretch A, I'm just going to do force A divided by K. And if I want to find stretch B, I just do force B divided by K. Sorry, I'm zoomed out a lot, so apologies for the messy handwriting here. Let's clean that up a little bit, but that's our process to get from our force into our stretch. And that's how we're going to approach this problem. So in summary, we start by free body diagrams. Then we're going to find our unit vectors for the force C, and then all the other ones we found direction because they're in those primary axes. That makes it a little faster. Then we do a sum of forces. We might have to do an equilibrium equation in some cases, but in this case, the Z direction only has that one unknown, the tension in cable C. Then we can use the tension in cable C to find FB and FA, and then we use the spring constant to help us figure out what the stretch in each of those cables or each of those springs is.